All right, good morning, everyone. Afternoon, good evening, good night. What? Yep, nope. Time is a strange construct. What we're looking at today is we're looking at the last part of chapter 22, which is non-linear graphs. So normally the things that we've been working on in further maths have involved straight lines that are perfectly straight and there's no wiggle room in them. However, life doesn't neatly fit into those things where everything's a straight line. So for example, population, this is a population chart that I've got here, covers a country from 1811 to 1981. And what I want us to think about is, well, what can we interpret from this graph? So I can look at this graph and any time between 1811 and 1981, I can line it up and I can find where what my answer is. So if I wanted to figure out, well, okay, I want to know what the population was in 1901. Well, if I measured up straight up from 1901, the rule is going to help me. So it's going to get to there. Now, I measure across. And then I measure across from there. So my question for you is, where is it? Where is it approximately? What's the population in 1901? So it's going to be a little bit less than 30. So I would say 29. Now, obviously, if our scale was a little bit more divided, and like I could see to the resolution of units of a million, yes, I could probably get the exact number, but I would say, 20-ish million. Now, if you guys remember, when we look back at statistics, there are two big words that we learnt about when we are interpreting data inside a data set and outside a data set. Two words that end in polation. So I've got interpolation, and what's the other one? And like some of you, totally extra. So interpolation means that we're looking inside the data that we have. Extrapolation is when we're looking outside the data that we have. So in this case here, the 1901 measurement that I have, what is it? Is that interpolation or extrapolation? I'm measuring inside the data set that I have on my graph, therefore it's interpolation. Now, if I was to look at this picture and I was to extend this to another point here, what would be the next marker? All right, it's going to be 1991. Now, I can look at that line and I can follow along that line reasonably well. So what I'm going to do is I'm going to use my graph and I'm going to make a prediction. So what I'm going to do is I'm going to line my ruler up. With this last little bit of my graph here. and I'm going to extend it. So I'm going to take my line and I'm going to put in an extension. And I'm going to put a marker there so that I can measure it, because what I want to do is I want to predict what the population on this graph would be in 1991. So if I go and I measure all the way back, and there's my mark there. So keep in mind that each of these is 10. Therefore, this next one up would be 60 million. So what's the population going to approximately be in 1991? Yeah, it's going to be about 55. So the 1991 pop Now, the question, though, is that interpolation or extrapolation? It's going to be extrapolation because I added to my graph. So I can say, oh, it's, it's a prediction. I can't say that's what it is because I don't know. I only had data from 1811 to 1981. The problem with some of these graphs, though, is the data points that we collect are not continuous. All right? Do you guys remember what everyone had to do on Tuesday? Every household had to do one. Yeah. So everybody had to do the census. And that happens every 5 years. And every 5 years are the only times that we know exactly how many people are in Australia at any one time. And they only happen every 5 years. So if you were to look at the census data for Australia, you might find that, I'm just going to use the same axis here because this is already neatly divided. But, we started off with, data here, data here, data here, and it slowly accelerates up over the years, Australia about now, if we were to go 1, 2, 3, Australia's population is around about 25 million there. But it's not a straight line, it changes over time. And what these data points are doing is they're helping us create a picture, to create a line. It's not a perfect prediction. The only things we know for certain are the census years. So every 5 units, we know pretty much, exactly what some things were. And then we can eventually get to the point where we have, so there's 2001, there's 2011, and then there's this year. And then we'll have a marker here and a marker here and a marker here for the in-between years. But, sometimes it's going to go up, sometimes it's going to stay, roughly the same, other times it's going to go up, It might go up there might be a big jump. You might get an influx of immigration or a high birth rate. But the idea is that you then try and connect your lines through your marks as best as you can. Now, actually, that's probably going to be a bad drawing, because our population growth is actually more like that. Maybe less extreme than that, but it is accelerating. Not quite exponential, but it's certainly accelerating. Our population is growing faster and faster all the time. I'll see if I can find the actual graph of this. But when we're making predictions, I have data for 1901 and 1905 and 1911 and 1906, etc. If I'm measuring between here and, say, this is 2016, if I'm using the actual data from the census and I'm trying to make a prediction inside my data, say if I wanted, 1954. So that's between census years. That's not a census year. And I wanted to make a prediction about the population. I can say, well, okay, it's between my census years, but if I look at just that section of the census line between my two data points, I can be a little bit more confident about my prediction being around about 12 to 13, about 14 million, than I can about the prediction from 2016 to 2021, because I don't have 2021's data yet. So even though I'm not using literal live accurate data, this prediction for 1954 is a better prediction than the 2016 to 2021 one, because I have the data points on both sides. Alright, so if I'm predicting between data points, that is far more accurate than me predicting between a data point and a future value or a past value. I could extrapolate and make a prediction about what the population was in 1896. I could just follow the line, so I could look at 1901 and 1906 and then just extend the line back on a similar gradient. And then I could go back and keep going and make a prediction about 1891. Further, and I could go further and further back to get to whatever time I wanted. However, the further I get away from my data, the more unpredictable or inaccurate it could be. All right, so this is a sort of thing that we call modeling. And this is how they can come up with these predictions, like Australia will have 40 million people by the year 2050, because they've looked at the data, they've seen how it's changing, and they can make accurate-ish predictions using the data, using interpolation and extrapolation, and going from there. What that means for us, though, is that there are sometimes questions where not everything lines up nice and neatly. So what I've got here is a question from 22C. And so I collected data for a particular type of tree. The data set gives the girth of a tree in centimeters at a particular age. So girth is the size. Using that data, draw a graph of the girth versus the age. All right, so we can't really draw a graph exactly, but what we can do, especially using our CAS, is we can actually use our friend statistics, enter all the top values in list 1, enter in the centimeters that we have in list 2, I cannot type today. And then I can draw it as a scatter plot. And I have a line there for me. If I was to draw that and I was to connect the dots, in fact, let's actually do that. Let's connect the dots. So I'm going to take my graph, so there's my graph. So I've got along the scale there, that's just years, 1, 2, 3, 4, 5, 6, 7, 8. And I've got a scale up and down the side there, so that's at 99. Now, it's kind of a straight line. It's not perfect. What shape of data would you say that is? What shape of line does this look like to you? If I was to, so let's actually connect the dots up. Yeah, it's got a very slight curve. Now I could break out all of my statistics knowledge and, you know, figure out which transformation's best. But, you know, if I try and measure between these points here. Hello, Miss Cancel.
Hello, how are you?
I'm alright.
Uh,
I'm recording this. So if you give me a minute, we'll talk after I'm finished.
That's fine. I'll come back.
Yep.
Okay, all right.
Now I have to edit that out. Go through, connect the dots as best I can, and I think you guys are correct in that there is a slight curve in here. And it gets more and more obvious the more I draw it. What's happening to the curve though? Is it flattening out or getting steeper? Yeah, it becomes flatter. So it becomes more steady. So from the graph, draw a graph of the girth versus the age. Well, there it is there. It's that sort of a line. Obviously, when you guys do it in paper, you would have properly labelled down, and up and down axes. From the graph, find the girth of a tree when it is 4 years old. So we've got 1, 2, 3, 4. So it's going to be about there. So it's going to be slightly more than 66.4. Now if I was to measure exactly, I would say it's probably almost exactly 70. And then if I was to find 80 along my axis and work across and down, I would find that it's probably around about 5.25 years. Because 80 is a little bit less than what the 5.6 is on the question. So the best part is that these sort of graphs have a name. Depending on the shape that type of graph has a name. All right, and what you guys may have seen before in your CAS calculator is when you do regressions, you have you have that long list of all the different types of regressions. So we're normally working with things like linear regressions. But in this case, this to me, because I know what I'm doing, looks like a logarithmic regression. And I can go in to my logarithmic regression and I can do a graph using a logarithmic regression instead. And it gives me something very similar to what it actually is. And the best part is I can trace along this regression line and make meaningful predictions with it as well. Think of it like a data transformation from Unit 3. That's what this is doing. It's taking the data, transforming it, and so if I go here at 4 years, it's saying about 72, which is fine. It's pretty good. So it doesn't quite exactly pass through all of it, but the regression equation allows me to predict things a little bit easier. So I'm going to finish up there.